to this fourth lecture in the Embedded System course. In the previous lecture, we started looking at the schematic diagram, also known as the block diagram, of one of the microcontrollers that belong to the AVR family. And we started looking at we wanted to look at the different pins and to, most importantly, to locate the CPU. So in order to locate the CPU on a schematic diagram, all we have to do is look for the ALU. And the ALU is here, so basically we can see that the CPU is here. So if we focus a little bit on the CPU here, we can notice that we have a program counter, a stack pointer, and these are from last year from the CA course. And then we have a bunch of registers for different reasons, and of course the ALU. We can notice the different other things. We're going to talk about them in more details in the upcoming lectures. As we said in earlier lectures, the AVR family belongs to the Harvard architecture in the sense of it has a dedicated memory for instructions and another one dedicated for data. So separate memories with separate buses. So feel free to pause the video whenever I ask a question in order for you to attempt to answer it, and then you can resume back the video. Alright, so what kind of advantage do we have with in Harvard architecture? It's definitely allows us to work in parallel. So basically, when we get an instruction ready to execute, once it started executing, we can fetch at the same time another instruction to get it ready to put it in the pipeline. And this is called a single level pipelining, right? And this allows us to do what? And I've talked about it in the previous lecture. Something that is special about the AVR core. Correct. So basically, this is the concepts that enables us to execute in every clock cycle. Hence, most of the instructions are actually executed in one clock cycle. Let's dive into more details about the timing, and what we're looking at here is a multi-cycle timing diagram. And take some minutes to analyze the timing diagram, so feel free to pause the video here. Alright, so what we're looking at is the clock rising and falling edges and rising back again. So this is what defines our cycles. Here we can notice that we have the very first cycle in instruction fetch. This is the very first instruction fetch. And then starting the second cycle, we can execute the first instruction that we fetched, right? And fetch the second instruction. Same is for the third cycle, where we can execute the second instruction and fetch the third one, etc. One can notice two things here. Someone can notice them. Alright, you should notice that first off, here we have some kind of slope and it's not perpendicular. So why is that? Alright, this could be related to the implementation, hence it's what happens in real life. So in real life there's some delay, some propagation delay in order to have the rising and the falling edges. Another thing that you can notice on this diagram is the execution, the whole cycle is a little bit beyond the borderline here. What would that be? What would be the cause of that? Alright, in order to find out, we're gonna focus on the execution. So the execution, as we've seen last year in the CA course, it could be divided into many sub-stages. First off, we need to read from the source registers. So this is what we, this is what we call getting the operands or fetching the operands, then feeding them to the ALU, and then once we're done with the operation that we're doing here, we need to write the result back into a destination register or somewhere. Hence, you can notice that this takes 1/3 of the time, 1/3 of the time, and 1/3 of the time. Right. So the particular subphase that is causing this, might look like an issue here is the writing back, but it's not exactly an issue. Why? Correct, because when I'm fetching back, getting operands back, as we seen in the CA course, the whole access to the register file is divided into two parts, into two subcycles, the writing and the reading. And we've noticed that we can, in a way or another, ending the writing back and starting the very reading. So basically here, once we've done with the writing back, we can directly start the reading here. Alright? And if you map this schematic diagram to here, you're going to find out that, if we're having another instruction that will follow, let's say here, those two here, they are the ending of the writing back and the beginning of the reading of the operands. They are somehow happening at the same time, and this is not problematic if we compare it to what we've seen in the CA course last year. Perfect. Alright, so one of the things that I did in the face-to-face lecture is to ask someone to analyze this particular screenshot from the data sheet. So these are the general purpose working registers, and you can locate them here. Alright, first question: what is the size of the word in a general purpose register in this particular CPU? You can either remember it from last lecture, or you can find out from the numbers here. So they go from 0 to 7. So basically we have 8 bits. How many total general purpose registers do we have? Well, we can notice that they go from R0 to R31, hence we have 32 general purpose registers. You should be able to notice two things here. First off is, unlike in MIPS, we have some addressing here. Why would that be useful? That would be useful because we can access anything using a base and an offset. What else can you notice on this particular picture here? You can notice that for the registers R26 up to R31, they have some writing here. If we analyze the writing, we can notice that we have 3 registers each is made out of 2 registers. So we have 6 registers divided into 3 registers. What's so special about the X, Y, and Z registers? Yes, so what's so special about them is the fact that we have a low byte and a high byte, and this should ring a bell from last year. So basically it feels like I'm having extra space in order to be able to represent my data. In what situation would that be useful? Let's find out. Alright, so these are the register, this is the register file, and they're directly connected to the ALU I've seen earlier, and there are 32 ones with 8 bits, and the 3 special registers are the are 3 big ones, and they use 6 registers, the last 6 registers of the register file here. And the fact that we are taking the register file is directly connected to the ALU, so basically we can directly take it, the operands from here into the ALU. Alright, so the 6 of the 32 registers that we talked about, the X, Y, and Z, they could be used as 16-bit registers in order to do some addressing, some indirect addressing, right? So of course, if you want to reach somewhere in the memory, for instance, right, with 8 bits, the maximum that you can reach is 2 to the power of 8, which is 255, correct? So if you need more, a bigger offset, you'll be needing more bits. Hence, you can use the X, Y, and Z instead of engineering it yourself in the application. So you can use the X, Y, and Z and the 16 bits that they provide you with in order to reach different places, right? So we usually use them in order to reach some addresses in the program memory especially. Alright, you should be noticing something that we didn't see in the MIPS ISA last year. What is it? Correct, there's a status register here. So what is it? The status register is directly connected to the ALU. So it has some information about the very last operation executed by the ALU. This is useful why? So if you remember from last year, the ALU had, of course, some connectivity with the upcoming stages of the pipelines, for instance, and the pipeline version of the MIPS. But then again, it had some information, some additional stuff. Those were the flags, correct? So basically, instead of having flags, we decided, separately here, we decided to include them in the status register, and these could be extremely useful for different operations, including the conditional ones. Alright, so the status register, also known as SRAG, if you see it in the data sheet, right, is updated after all ALU operations. So this is great because instead of like last year, in order to know whether to branch or not, we needed to do some branch if equal to 0 or branch if not equal, or etc, right? We don't need anymore the need of using dedicated compare instructions. All we have to do is go ahead and read a particular field in that particular SRAG. Alright? So this is definitely more compact codes, and it is definitely faster. Why is it important to have a compact code? Because remember, in the context of embedded systems, we don't have a lot of resources, so we don't have a huge memory size. Okay, so this is what the SRAG looks like in the datasheet, and you can notice the different fields in that SRAG. How big is it? Well, it is, the different fields are, and the bits are from 0 to 7, so basically it's an 8-bit register as well, and it makes sense because it's the whole general purpose registers, etc., and everything operates in 8 bits here. Alright, so you can notice two different things here. First off is the read and write. So this is an information about whether this particular field can be written or just read, or you have both accesses to it. Right? And then you can notice something else here, which is the initial value, and here it's fixed to 0. Why is it important to have an initial value, fixed initial value here? So upon reset, for instance, you want your microcontroller to start fresh from a stable state. So basically this provides you with a stable state. What would happen if you had random values here? If you have random values, you cannot guarantee that you're going to be in a stable state. Alright, so you're going to have more details about the SRAG, and you're going to work with it in the upcoming tutorial. Great. One of the things that we've seen in this face-to-face lecture as well is how the memory is organized from a logical point of view. So these are logical representations of how to deal with data and how to deal with the program. So I'm going to start with the data first. So we've seen that we have 32 general purpose registers, and they had addresses. So register R0, for instance, has the address of 0x00. Register 1 R1 would definitely be 0x0001, for instance, etc., all the way up to the 31st one, right? Then we have a bunch of registers. These are not general purpose registers, and you can guess it from the name. It's IO, so they are for input outputs. So basically you should sense that this is where you're gonna these are the registers that you're gonna use in order to communicate with the environment, interact with the environment. You're gonna write data to them that is meant to go to the environment, and you're gonna read data that the environment will provide you from those registers. And we have 64 of them, again with a addressing scheme here. Then you have some kind of extension that is useful in different microcontrollers, but these, again, they are extended IO registers. For some reasons you might need more input outputs. It's not an important detail for now. The most important one is the internal SRAM. So the internal SRAM is seen as a continuity from the logical point of view, continuity to the registers that we have here, with the addressing here. Alright, so remember the SRAM is used for the data as a data memory. Question number 1 is, this is a physical implementation, so are the registers part of the SRAM? The answer is not. Definitely not, because the registers, they belong to the CPU, and the SRAM, we've seen it before in the previous slides, that it's a memory that is outside the CPU. Alright, perfect. So if you go to the program memory now, one can notice that it has a size. What is the size of it? Well, as I said in the previous lecture, that from the naming convention of the Atmega, we can see that in the suffix here we have 32, and 32 is an indicator about the flash memory size. So it's 32K. What would be the program memory in an Atmega 16 something? It would be 16K. Perfect. Alright, so if I go back to the data memory, we know that the size of a word is 8 bits, right? It's exactly as the registers. Make sense? Yes, it does. Right. Now the program memory, I'm trying to guess the word size. So in order to guess it, well, we're gonna do something better. That is, we're gonna use the information that we have in order to have the exact size of the word here. So all we have to do is take the last address, right? So this is the address of the different words here. So all we have to do is get this address and use the memory size in order to know the word size. So whatever 0x3FFF is in decimal, right? All we have to do is divide 32 by this address to get the size of the word. And you're gonna notice that the size of the word is 16 bits. So this should give you an indicator about the size of the instructions. So what would be the size of the instructions when it comes to AVR? especially the Atmega 32, let's say. Alright, so normally minimum a size of an instruction would be the size of the word in the program memory, that is 16 bits here. And this is true for most of the instructions. Some instructions have more size, so we're gonna we could divide them into two words. Alright, so let's go back to the block diagram that we have here of our microcontroller, and we're gonna go and check the pins. So you can notice that the pins are the things that are outside the microcontroller, that allows us to go outside the microcontroller. So we can see here the VCC, alright, and we can locate it here. Alright, so this is the supply voltage. Then we have the ground here. Then we can see the reset button, and it's connected to the MCU control, and the MCU control is the microcontroller, right? So this is what controls the microcontroller. So here we can reset it to a stable state, the original initial state. Alright, and then you can see XTAL1 and XTAL2 here, and these are connected to the internal oscillator, also known as the internal clock, right? And then we can connect them to an external one, as people did on the Arduino Uno board, for instance. They connected it to an external resonator. And then we have the AVCC, and this is the supply voltage for my ADC, my analog to digital converter, which is also connected to the ARAF. And you should remember the ARAF from the previous lecture. Correct? It is the reference pin for the ADC. So if we need more resolution for a particular sensor, this is what we need to apply some voltage to. This is what we're gonna use. Alright, usually you should check the data sheet whenever you're gonna use an ARAF, so what to do with the AVCC, and when you're not using the ARAF, the AVCC should be connected to what? Usually it should be connected to, let's say, a capacitor, and then to VCC, let's say. Alright, so the last things that we want to talk about are the ports that will enable you to communicate with the outside. So port A is what serves as analog inputs, so they're connected to the ADC. This is the only port that is connected to the ADC, so whenever you're going to use some analog inputs, you're going to use port A, the pins on port A. And whenever you're not going to use it for the analog feature that it has, you can use it as a normal 8-bit bidirectional I/O port. So basically input-output digital one, and they're connected to internal pull-up resistors. And we talked about pull-up resistors in the DSD course. Do you remember we used them for what reason? So the reason for pull-up resistors, or pull-down sometimes, they're used in order to avoid shortcuts and to protect the electronic device. Alright, so port B and port C and port D, they are all 8-bit, again, bidirectional I/O ports, and they have some special features. Right, so special features for the Atmega 32, it is for this particular microcontroller, and for the other microcontrollers you should always get your data sheet, and we're gonna find out what those special features are later on. So you can notice port C has something related to the JTAG interface, and I believe that you've seen JTAG in the second tutorial, but we're gonna talk about it in more details in the upcoming lecture. And then again, port D, it has some special features, and we're gonna see them in the very next slide. Alright, so in addition to the bidirectional I/O pins, we have an alternate function, and those functions are different for each port, right? So I want you to notice something here. So for instance, in port B we have this pin that is connected to a non-competitor that can't be found anywhere else. And then you can see that port C, as we said earlier, that those pins are connected to the JTAG. So if you want to use the JTAG interface, you have to go through those pins in port C. and sometimes something that we're gonna see whenever we're gonna talk about the communication between the different embedded devices, the two wires serial bus, also known as I2C. Alright, and the last thing that you should notice is the TXD and the RXD. And if you remember the picture from the Arduino Uno board, it had two LEDs named TX and RX, and I said that they flash whenever we're sending something outside the board or sending something to the board. So basically it seems like they're physically connected on the board to those two pins of the Atmega microcontroller. Alright, this is where I stopped with the people from the face-to-face lecture. Of course, they had many questions. If you have questions, maybe you can ask them in your next face-to-face lecture. Thanks for watching and listening, and see you soon.